Everybody, I'd like to walk through a script today that I think it simulates data that's very similar to the data that we have on crime incidents and geolocations. So it'll do a lot of the stuff that we're doing, but I think seeing it in a simulation is nice because it helps us understand, kind of what the parameters are. And especially when we go to quantitative analysis of the data, we've been spending, all the time doing data wrangling. As we transition now, as our wrangling is getting um, more towards the end and we're pretty clear about what we have to do, we can start transitioning to analysis of the data that we have. And so sometimes when you're doing analysis, it's good to have a really good idea by simulating the data set so that when you do analysis, you already know what the results should be because you've simulated it, and you can see whether your analysis is delivering what you expect. The analysis of spatial data is complex. We have an even more complex data set. We have a panel of spatial data. That is, we're observing spatial units over time. The econometrics and other kinds of analysis of panel spatial data in the setting that we have, which we would typically call a staggered difference in difference. That is, different geographic units, hexagons in our case, are being treated at different times with homeless shelters or homeless encampments or other policy interventions. Um, so that's a area where the econometric analysis of that is definitely at the frontiers of econometrics. We're going to be doing basic stuff with that, but even the basic stuff is not obvious, typically not taught at undergraduate level, often not even taught at the graduate level. So we'll start looking at how people do this, and a nice way to understand what people are doing is by having a simulated data set. So this will be hopefully our reference set, data set for when we're thinking about analysis. We'll be saying like, let's use our simulated data set to do it. So let's see how the simulated data set works. So we have a few packages to load here, including a color package, Viridis Light. I think I'm going to use it later on. You may have to install some of these packages, but the other ones are familiar. Since we're simulating data, we set a seed so that every time our simulation runs, it always generates the same numbers. So we set the seed. You can ask AI to explain set.seed and understand it a little bit more. Then we're going to create a square base area and give it a projection system. And then what we're going to do is, uh, well, we'll just have a little code here. That's our base area now is we might think of it as just sort of the area that we're going to be looking at. Then we're going to make squares on this base area. So I'm calling them BG because they'll be the equivalent of our census area block groups. So the larger areas that we have, and we'll have these larger areas and then we'll overlay hexagons on them. So here's the command to make our grid of base areas. Then we're going to think of them as a block group. We're going to add in a few variables that we're just going to create randomly for each one of these grids. So we're going to for each one of the squares, we're going to have a variable proportion black, median income, and whether it's in the urban core. So a binomial variable 0, 1, we'll call that an urban core. So we'll imagine sort of a big city and it has lots of little downtowns in it. So we'll just randomly scatter these urban core around our block groups. Um, so we can map this using tmap. So this is what our city, we can think of it, or a set of cities looks like. We have 400 little squares, and some of the squares are urban core, and some of them are not. So that's just a random sort of beginning. Now we make our hexagons that we overlay on top of our city, and then we can run. A visualization here. Notice I'm using ggplot instead of tmap. So two alternative ways to do mapping. Uh, when I first started, I started doing ggplot in R, but tmap seemed to be more powerful and better than ggplot. So in this script, I'm going to go back and forth between them. The syntax, the latest TMAP is TMAP version 4, and they've adopted some of the syntax from the tidyverse, from sort of ggplot, to make them more comparable. So it may be that in the end, the two, gradually start merging. Um, yeah, so that's the ggplot version, and then here's the TMAP version. So you can see they're, sort of if we go back and forth, they're pretty much giving us the same thing. I just have the colors different here, obviously. Um, so that's our basic map. Now, you notice that the hexagon overlays, many of the hexagons, for example, this one right here, are half in one block group, half in another block group, and some of them are straddling, like here, they're straddling four block groups. So we want to compute area weighted averages for the hexagon, so we already know how to do that. We'll do the intersection of the block groups and the hexagons, and then we'll compute the area of each one of those intersections, and then we'll compute weighted averages of those variables, urban core, prop black, and median income, for grouping by the hexagons. So now each hexagon will have a new value for these block group characteristics. That's the weighted average, depending on how much of the hexagon is in each block group. So we merge that back in to the hexagons, and then we can map or plot that. And now we see that the hexagons are gradated. They're not just two colors anymore. Now we have a continuous set of colors. And so here are the hexagons, the urban core. So what I'm mapping here is the urban core value. Most of them are not urban cores, so they're black. That's the 0 value. And the ones that are around the urban cores right in the middle, the hexagon is fully 1. But if you're a hexagon that's straddling two block groups, one of which is urban core, one is not, then your hexagon now is partial value between 0 and 1. So we can do the same thing for TMAP. Um, and Notice that I filtered out the hexagons that are missing, because there's hexagons at the end here that are missing. Um, Not sure why these ones are coming out here. Something to explore. All right. So now we're going to create a panel. So that's our basic cross-section of the hexagons. But now what we want to do is make a panel out of this. So we'll first just replicate the 2015 one. We'll call it 2015. Take away its geometry, and then create a dummy variable for whether the hexagon is in the core, by saying if the hexagon has above 0.75 in the core, we'll call that a core hexagon. So we're just creating a new variable for each hexagon, whether it's in the core or not. You'll see why we do that in a second. So let me run these again. And then we are going to create some preliminaries. So we'll have the years run from 2015 to 2004. We'll create a blank list. We'll put the 2015 data as the first data frame in the list. We'll add a variable year to that data frame. We'll add a value for shelter equals 0 to that data frame. And then we'll create a crime incident variable in just that data frame. So here's the subset of the list saying do this only for data frame 1 in the list of data frames. And we'll create a variable crime incidents, and it'll just be related to the proportion black in the hexagon. And remember, these are incidents, so we're not, we're just doing a sociological thing. These are correlations. We'll have it negatively associated with income and positively associated with if the hexagon is in the urban core, and then we'll add some random noise, one value for each row, so a different random level, uniform value from between 0 and 1. So that it'll always add, but small amount or a large amount. So we'll draw from the uniform distribution. So we run that. I think maybe I should run everything again, because I can't remember if I ran it. So there we go. Now we're going to simulate for the years for from 2 to 2024. So the length of years is probably 10, right? Yeah, so we see that the length of years is 10. So we're going to go from 2 to 10, and we're going to um, uh, call the previous data frame in the list. So I minus one. So if we start at two, this would be two minus one, which would be one. So that'll be the previous data frame. In this case, it would be 2015. Then we'll create a new data frame that will, to start with, will just be the same as the earlier data frame. Then we're going to have some of the hexagons get a shelter with probability 2%. So we're going to draw from the binomial distribution, which is the 0, 1 distribution with probability 2%. We're going to, for each hexagon, we're going to say, are you going to get a shelter? This is should be 2% chance. For each hexagon, are you going to get a shelter or not? And that'll be then a new variable in the shelter is whether you get a shelter or not. Then we will create, what we're going to do is take our base variables for income and proportion black, and we're going to have them changing over time. So for each time period, we're going to draw some noise. We'll call it noise one and noise two for income, and then noise one and noise two for the proportion black. And we're just going to draw from the normal distribution, mean a very small number, standard deviation pretty small. So what we're going to do is just every year the income in that hexagon changes by a little bit, and the proportion black changes by a little bit. We're going to have the proportion black going down, so gradually declines. You know, the San Francisco Bay Area notoriously has seen a decrease in the proportion black in many of the cities, San Francisco most notably. So that seems to accord maybe with what we observe at the city level. We could have some hexagons increasing and others decreasing over time. Obviously, that might be as cities are sort of resegregating, that might be the case. These are all assumptions that we can make, right? That then the nice thing about simulating data is you already know what you should be observing, and that's the virtue. And then we'll update our median income and our proportion black in each case by having it be uh, since new DF is old DF, so we start with the old DF, but if you're in the core, then you'll change differently than if you're not in the core. So here, if you're not in the core, we have income rising faster than in the core. So it's sort of like the downtown cores are declining in income is the pattern we have here. And again, right? Probably in most cities, some of the cores are rising in income and other of the cores are declining in income within the city as neighborhoods change. Here, we're just going to say they all change in the same direction. So we're looping over the years. So we'll just run this, and what we get then, we can see now we have, where is it? Uh, Hex list is a large list of 10 elements, one data frame for each year. We can name each one of those elements to a data frame by adding in the year there. So now if we look at the list of data frames, we see that each one has a name and then each one has the variables. So we can now compress all of them to create a data frame. So here's our 38,000, right? Each one of the 3,886 hexagons is being observed 10 times. So that's our panel data set. We can bring back the geometry to the panel data set here, and we'll define it as a SF. So we see by looking at class that it is an SF. And we're going to create a new variable called year number that's going to be numeric and then turn year into a factor variable. Can't remember why I was doing that, but it's useful. And now we can do a facet wrap plot of the shelters. So we'll have the geometry of our city, and we can see nicely 2015, none of the little squares have shelters. As we go through the years, there's more and more shelters, and you can run this at home and see it bigger. You'll see by 2024, we have Remember, it's 2% every year. So for over 10 years, by 2024, about 20% of the shelters have, um, of the squares have years. And it once the way we have it structured here is once you get a shelter, you always keep the shelter through subsequent years. So in our data sets, right, some of the shelters are closing over years, so some of them are sort of turning on and then turning off, but we'll keep them simple and just have once you get a shelter, you always have a shelter in your hexagon. We can also plot it with the proportion black. I won't do this because it takes time. Here's the T-map version of plotting the same kind of facet wrap. You can see that they've done the same thing with T-map now, and you have TM facets to basically do the same thing. Now what we'll do is since we have panel data set, we're just going to look at over the years. We'll group by year and whether you're core, and we'll plot the average over the years. So we'll plot this, and then so we'll first summarize, and I think yeah, then we'll plot how the time trend, the average crime incidence over years is going. And so, if you're not a core, crime is lower. If you are a core, crime is higher, and crime is declining over the years. So that's just our setup is that crime is declining over the years. The crime incidents are declining over the years. We can, yeah, so here's our 10 years, 3,800 hexagons per year. Now we'll find for each of the hexagons when it first gets a shelter. So we'll call that the event year. When did the hexagon get a shelter? So that'll be a little data set of 134 observations. So if we click on that, we can see each hexagon ID. We can sort it here. Hexagon 116 got their shelter in 2018. Hexagon 413 got their shelter in 2016. Hexagon 675 got their shelter in 2024. So each year, so each hexagon that got a shelter, when did they get a shelter? We merge this back into it, and then we'll just keep the shelters that happened between 2017 and 2021 so that we can have 3 years before and 3 years after. So we'll create another little data set, and then we'll we'll define a variable called the event window for whether you're in that 3 years before, 3 years after. And then what we'll do is average up the crime incidents in the event window 3 years before, 3 years after. You'll see in a second why we do that. And then we'll plot what happens to crime incidents over time. So we see that before the event of getting a shelter in the hexagon. So this is only the hexagons that get events and get events between, I think it was 2017 and 2021, 3 years. So then we'll be asking what happens 3 years before and 3 years after the event. So the event is 0, but for different hexagons, it could be different time periods. So for some it's 2024, for some for 2021, for some it's 2018. But what we see is crime incidents are declining when they get a shelter, because the way we simulated it here is we have a positive effect. So when they get a shelter, crime incidents go up. And then because they have a shelter continues over time, they continue on a higher trend. It's still going down, but the trend has been shifted up. So we're just validating, that the simulation that we're doing is indeed showing up in the data. There isn't so much noise that it doesn't show up in the data. Then we'll do that for the panel. So, excuse me. Well, for all the panels, we're going to draw a line for every shelter. And we'll go down here and we'll see for the hexagons that never get a shelter in this time period, then there's no jump. But then we can see for 2016, we see the jump in 2016. It suddenly goes up. For 2017, the trend is down and then it jumps up. For 2018, the trend is going down, but then in 2018, the crime incidents go up. For 2019, the trend is going down, but in 2019, it jumps up. For 2020. So now we're looking at fewer hexagons in each one of these things, and there is random noise for the crime incident, so it's not a perfect jump of the same amount every single time. We see that, there's some randomness to this outcome variable of crime incidents. So that's our panel data set that we now have, very similar, hopefully, to the panel data set that we are developing in the real world. And this will be nice for doing analysis.